In this video, we are going to study tension and equilibrium using suspended traffic light as our main example. At first glance, the traffic light looks simple because it is not moving. However, a stationary object can still have several forces acting on it. The important idea is that these forces must balance. The traffic light has weight pulling downward, and the cables pull upward and sideways through tension. If the traffic light remains at rest, then its acceleration is zero. According to Newton's second law, that means the net force must also be zero. So the question is not, are there forces acting on the traffic light? The question is, how do those forces combine so that the total force is zero? By the end of this example, we will use the angle of the cables, the mass of the traffic light, and Newton's laws to calculate the tension in each cable. Before solving the traffic light problem, we need to understand what tension is and how ropes and cables transmit forces. Tension is the pulling force transmitted through a rope, cable, string, or similar object. The key point is that rope and cables can pull, but they do not push. If you pull on one end of a rope, the rope transmits that pulling force along its length. In an ideal physics problem, we often assume that the rope is massless. This means the rope itself does not require a net force to accelerate any part of its own mass. Because of this idealization, a massless rope transmits the same tension from one end to the other without changing the magnitude. On the other slide, the diagrams show that the tension force acts along the rope. The direction of the tension depends on the object we are analyzing. For example, if the rope pulls on a block, the tension force on the block points away from the block along the rope. At the same time, the block pulls back on the rope in the opposite direction. These opposite forces are related to Newton's third law, but they act on different objects. This is why we must be careful when drawing free body diagrams. We draw only the forces acting on the object of interest, not the forces that object exerts on other objects. In many real systems, ropes pass over pulleys. Let us see what happens to the tension when the rope changes direction. Now consider a rope passing around a pulley. In this example, we assume the pulley is massless and frictionless. These assumptions are important. If the pulley is frictionless, it changes the direction of the rope without reducing the tension. If the rope is also massless, then the tension is transmitted throughout the entire rope. So the rope may bend around the pulley, but the magnitude of the tension remains the same on both sides of the rope. This is why we often label both sides of the rope with the same tension, capital T. In ideal pulley problems, the pulley changes the direction of the force, but it does not change the size of the tension force under these ideal conditions. This is a useful simplification. In real systems, pulleys can have friction and mass, but in introductory problems, we often begin with the ideal model so we can focus on Newton's laws. Now that we know how tension acts, we can apply it to objects that are not accelerating. This brings us to equilibrium. An object is in equilibrium when it has zero acceleration. This does not necessarily mean the object is at rest. An object moving with constant velocity also has zero acceleration and can be in equilibrium. However, in this example, we will focus on static equilibrium, where the object is at rest. From Newton's second law, the net force equals mass times acceleration. If the acceleration is zero, then the net force must be zero. For motion in two dimensions, this condition must be true in both directions. The net force in x direction must be zero, and the net force in y direction must also be zero. In symbols, we write the sum of the forces in the x direction equals 0 and the sum of the forces in the y direction equals 0. These two equations are the foundation of the traffic light example. The horizontal force components must balance each other, and the vertical force components must balance the weight. Let us now apply these equilibrium conditions to a real two-dimensional force problem. We are given a traffic light with a mass of 15 kilograms. The traffic light is suspended from two cables. The left cable makes an angle theta 1, which is equals to 30 degrees, and the right cable makes an angle theta 2, which is equals to 45 degrees. We are asked to find the tension in each cable, and we are told to neglect the masses of the cables. Let us pause and think about what is physically happening. The traffic light has weight pulling downward. The left cable pulls upward and to the left. The right cable pulls upward and to the right. Because the traffic light is not accelerating, the horizontal components of the two tension forces must cancel. Also, the vertical components of the two tension forces must add together to balance the weight of the traffic light. The two cables' tensions do not have to be equal because the cable angles are different. This is an important prediction. Since the right cable is at a steeper angle, it has a larger vertical component for the same amount of tension. The calculation will show exactly how the two tensions compare. Now we draw the free body diagram for the traffic light. The system of interest is the traffic light itself. That means we only draw forces acting on the traffic light. There are three forces acting on it. First, the weight W acts straight downward. The magnitude of the weight is mg. Second, the left cable exerts a tension force T1 on the traffic light. Since tension pulls along the cable, T1 points upward and to the left. Third, the right cable exerts a tension force T2 on the traffic light. This force points upward and to the right. We also choose coordinate axis. Let positive x point to the right and positive y point to the upward direction. With this coordinate system, the weight is negative in the y direction. The horizontal component of T1 will be negative because it points left, and the horizontal component of T2 will be positive because it points right. And the free body diagram will look like this when you draw it. Now we break the two angle tension forces into components. For T1, the cable angle theta 1 is measured from the horizontal. That means the x component is adjacent to the angle and the y component is opposite to the angle. The magnitude of the horizontal component of T1 is T1 cosine theta 1. Since it points left, its x component is negative. So we write T1x equals negative T1 cosine theta 1. The vertical component of T1 points upward, so it's positive. We can write T1y equals positive T1 sine theta 1. For T2, the angle theta 2 is also measured from the horizontal. The horizontal component points to the right, so it is positive. T2x equals positive T2 cosine theta 2. The vertical component points upward, so it is also positive. So T2y equals positive T2 sine theta 2. The weight does not need to be split into components because it already points entirely in the vertical direction. So the weight has no x component and its y component is negative mg. This component step is where many mistakes happen. The sine and cosine choices depend on where the angle is measured. Here, both angles are measured from the horizontal. So cosine gives the horizontal component and sine gives the vertical component. Once the components are identified, we can translate the equilibrium condition into two equations. When you solve a problem with forces, it is easier if you create a table indicating all the forces and its x components and y components separately, like you have here. Now, if you look at the first column, we have all the forces. In the second column, we have the x component of all these forces. And in the third column, we have the y components of all the forces. Now, we can put in the values we found in the previous slide in here. And you can see to find the net force in the x direction, we can directly just add these things together and get our equation number 1. So we get negative t1 cosine theta 1 plus t2 cosine theta 2 plus this 0, which is not shown here, equals to 0. So this is the equilibrium condition in the x direction. So this is our equation number 1. And we do the same thing in the y direction. So we have the net force in y direction equals to t1 sine theta 1 plus t2 sine theta 2 minus mg, and that is equals to 0. So this is the equilibrium condition for the y direction. Now we have two equations and two unknowns. So the next step is to solve these two equations to find t1 and t2. Now to solve this equation, let's select equation number 1 and then rearrange it. So what we can do, we can bring this negative t1 cosine theta 1 to the other side of the equation where we have this 0. So we get t2 cosine theta 2 equals t1 cosine theta 1. And from here, we can find what is t2. So t2 is equals to t1 cosine theta 1 divided by cosine theta 2. So let's use this as our equation number 3, and then let's substitute this into our equation 2. So we get t1 sine theta 1 plus t1 cosine theta 1 divided by cosine theta 2 times sine theta 2 minus mg equals 0. Now you can see in this new equation, the only unknown is t1. So we can solve for t1 from here. Now we can simplify this further. So we have t1 sine theta 1 plus t1 cosine theta 1. And here we have sine theta 2 divided by cosine theta 2, which is equals to tan theta 2. And then minus mg equals 0. So we can send this negative mg to the other side of the equation and we can factor out t1. So we get t1 times sine theta 1 plus cosine theta 1 tan theta 2 equals mg. So t1 equals mg divided by sine theta 1 plus cosine theta 1 tan theta 2, and then we can substitute the values. So m is equals to 15 kilograms and g is 9.8 meters per second square divided by sine 30 degrees plus cosine 30 degrees tan 45 degrees. So we get T1 is equals to 107.6 newtons. And then we can use this equation that we found earlier, T2 equals T1 cosine theta 1 divided by cosine theta 2, and substitute the value of T1. So we get 107.6 times cosine 30 degrees divided by cosine 45 degrees, and then this is equals to 131.78 newtons. So we can write down the final answer. T1 is equals to 108 newtons and T2 is equals to 132 newtons.